So the first thing, if you notice on the screen, I just got a message from our calc tutor, Aaron Nitz. There will be a special study session held on Thursday evening from 7 to 9 p.m. So that's available to you as a possibility. Thursday, 7 to 9.
Is that in the library, like the normal tutor spot?
Yeah, I believe. Have any of you gone to one of those sessions? I believe it's right near that. You know, when you come in the main door of the library, that area to your right.
Yep, it is. Yeah.
Yeah, that's what I thought. Okay.
I just didn't know if it.
Yeah, well, I didn't get any message, so it must be in the standard place. Yep.
Okay. Sounds good.
Sometimes what you'll do is go in the classroom, but I didn't get that message, so I don't know. Okay, well, before we begin review, the big thing that we need to talk about is 2.5 homework. So I'm getting the message that there are some questions out there, so let's get that started.
At some point, if we could go through 64, we don't necessarily have to do that one first, because that's not necessarily of most importance. But unless someone else has other questions.
Yeah, well, here's number 64. This is kind of an interesting question.
Yeah. Because
it relates to real thing. It's Einstein's theory of relativity. Mm-hmm. And this is the one of the formulas related to that. And you can see m sub 0 stands for the mass of an object. Mm-hmm. V, velocity, and c is the speed of light. So the question is, find the limit of the mass as v approaches c from the left. So notice I wrote down the equation. This is just a copy of what's in the problem, and then I wrote the limit as v approaches c, left-hand limit. Uh-huh. Okay, so when v gets close to c, but c is just a little bit less, right? Mm-hmm. So what happens when you take something and divide by something a little bit less than it? I mean, like for example, 7 divided by 6.9999.
And it gets close to 1.
That's right. And so you notice I wrote almost 1.
Yeah. Okay.
Yeah. And then what happens when you do 1 minus almost 1? It's going to be really tiny, right? Almost 1 could be like 0.99999. Right?
Yep.
And when you do 1 minus something like that, you're going to get this incredibly small number. Do you get that? Mm-hmm. So in the next step, then you take the square root of a small number. Well, it's still going to be a small number. And it's a small positive number. Yep. Okay? And again, it's really a tiny number. And what happens when you take anything and divide by a real tiny number?
You get a big number.
Yeah, so ironically, think about this. What his theory actually states is if we could approach the speed of light, of course, it doesn't look like we can, but if we could, mm-hmm. our mass would become infinite.
Okay.
Maybe that's just a demonstration that, we're not going to be able to do it. I don't know. But anyway, that's what 64 looks like. And I know this doesn't look like math to you, but this is kind of what I mean is this almost baloney and this tiny baloney doesn't look like math. But again, it's the way you need to deal with these limit problems. Mm-hmm. Get rid of the pictures here. Another question on 2.5.
Number 45.
All right, 45. Let's go to the homework. Okay, 45. The limit of x squared plus 2x, plus 2 over x plus 4. The limit of that as x approaches negative 4 from the left. Negative 4 from the left. Or is it positive 4? Could somebody check?
-4.
Okay, it looks like I didn't write that over here. But anyway, all right. So as x approaches negative 4 from the left, that means it's like negative 4.1.
Yeah.
Yeah. So what's going to happen when you square negative 4.1? Well, it's going to be about 16. So that's this part right here. And when x approaches, negative 4.1 is going to mean we're going to have what, a tiny negative on the bottom of this?
Yeah.
And 2 over a tiny negative is going to be
number.
Is going to be negative infinity. It's going to be a negative huge number. And then what happens when you add 16 to a negative huge number? Well, the negative huge number will overtake it.
Okay.
And so final limit, negative infinity.
Okay. Thank you.
You're welcome. Other questions on from the 2-5 homework? I'm happy to go through more if you just have some more.
Oh, 49 as well.
All right. Yeah, there's 49. The limit of e to the x over x minus 8 quantity cubed as x approaches 8 from the left. Okay. Well, on the top, you're going to have e to the 8th. On the bottom, what's going to happen as x approaches 8 from the left, that means something like what? Negative 7.9-ish? Positive 7.9-ish. And what's 7.9 minus 8?
0.1.
A negative, right?
Yeah.
And then what happens when you cube a negative? It stays, it's a negative cubed is still going to be a negative.
Yeah.
And in fact, it's going to be even tinier. So here's my analysis over here on the right. So you got e to the 8th on the top over a tiny negative. Well, first of all, a positive divided by a negative is a negative.
Mm-hmm.
And a huge number divided by a tiny number is going to be a huge, so this is going to be negative infinity.
Okay.
Oh, I do. Travis, got some. Can you unmute me? Maria, sure. Sorry, Maria. I did not mute you, by the way. No. Oh, you know what? I can hear you. Can you turn your volume up? I can barely hear you squeaking away there. But no help. Still coming through real quiet. Yeah, Travis, thanks for the comment. That's better.
I can hear you a little bit now too.
So
I have a question.
Okay.
So the one we just went through, or for other ones too, how can you tell that it's infinity and that there's not just a hole in the graph? Like, what's the difference between those two?
There won't be. Okay. Well, first of all, we don't have any possibility of the denominator being 0. So there's really no chance of there being a discontinuity. And the only time you'd have a hole, well, we got all kinds of echoing now, but anyway, the only time there'd be a hole is when something on the bottom would cancel with a factor on the top.
Okay. That makes sense.
So really, you don't have to, because there's no zero on the bottom. I know it's really tiny, but it's not going to be zero. Then we don't really have a problem. You don't have to worry about a discontinuity.
Okay, so only if you can like factor something out and then cancel it out. That's the only like the way.
That's the only time a hole occurs.
Okay.
Yeah.
And also, could we go through 51 and 53, please?
Sure. Yeah, I'm getting feedback from myself here. Okay, 51 on the screen. So you're supposed to take the limit of the natural log of the absolute value of the cosine when x approaches pi over 2 from the left. Okay, so let's to make that a little more understandable, what's pi over 2 in degrees?
90.
Yep. So we're approaching 90 from the left. So in other words, we're at like 88, 89 degrees, okay? And what happens when you're taking the cosine of an angle and it gets closer and closer to 90? So this is a trig issue right now. The cosine of an angle close to 90. Well, at 90, the cosine turns out to be 0.
So it gets closer to 0?
Yeah, so when you're getting closer, yeah, exactly. It's getting real tiny, okay? All right, and then when you take the absolute value of that, well, it's still tiny. We were already in the first quadrant, so that absolute value doesn't really do much. Now, what's the natural log of a real tiny number? So once again, what you're actually thinking about is e to what number is a real tiny number?
To a negative?
Well, yep, negative, definitely, because a negative exponent makes it smaller. And it's going to have to be a negative huge number. You know, it's going to have to be like e to the negative 2 trillion to make it really small. And because of the, you know, really small, negative infinity. So, I don't know. Let me know if that didn't do it.
Can we try 53 too?
Yep. So 53 says x is approaching 1/2 from the left, and the expression is x times the secant of pi x. Okay. So you can half substitute here. As x is approaching 1/2, it's just a little less than 1/2, like 0.49 or whatever. But it's going to be approaching 1/2, so I can make this substitution right there, x 1/2. And what's going to happen to this trig function? Well, if it was 1/2, then that angle would be pi over 2. Okay? Right? 1/2 times pi is pi over 2.
Okay.
Now, the secant of pi over 2, well, the secant is the reciprocal of the cosine. So the question is, what's the cosine of pi over 2? Well, it would be 0, and you can't take the reciprocal of 0, but it's not quite 0. It's like really tiny number. And what's the reciprocal of a really tiny number? The reciprocal, what's 1 over a tiny positive? It's going to be approaching positive infinity, this number right here. And I know this looks like bad arithmetic, but 1/2 times infinity, a positive infinity, would still be, it's still going to grow without limit. So now I went through a bunch of arguments there. I wish I wouldn't get, I'm getting bad feedback. Evidently it must be from your computer, Maria, but hopefully everybody can still hear me.
Yeah.
So any of those arguments didn't make sense, let me know.
Could you go over 51 one more time? I'm not quite understanding that one.
Yeah, 51. Anybody else on 53 first? All right, 51. So our angle is approaching 90 degrees from the left. So that means it's like close to 90 degrees, but positive. So like 89 degrees or so. What's the cosine of 89 degrees? It's really tiny, right?
Yeah.
And what's the absolute value of a really tiny positive? Well, it's still going to be really tiny. And
Yeah.
so now the question is, what's the natural log of a tiny number? And that's where you look over here to the right. What does natural log mean? It means e to a power equals this tiny number.
Yeah.
So you got to imagine now what goes in the box. Well, if you put a big number in there, that's going to be huge. So that's not it.
Mm-hmm.
If you put a negative exponent in, that'll flip it upside down. That'll make it tiny. So negative, big, a negative big number goes in that box.
Okay, I think I got lost again. Well, I followed you, but then I still got confused of when you know it's supposed to be well, like after you did like the natural log is like e
Equals a natural log of a tiny number.
No, I understood that part. It was like the part before I kind of got confused.
Okay. So as x gets closer and closer to 90 degrees from the left, the cosine is still in the first quadrant, and so it still has to be a positive. And it's got to be really dinky, right? It's going to be really small.
Yeah.
So a positive small angle. When we take its absolute value, well, it's already positive, so that didn't really do anything. So it's still a tiny number.
Oh, okay. That makes sense.
And then, all right, what's the natural log of a tiny number? And then that brings us over to here. And now you've got to just imagine what can you put in the box to make e to that power be tiny, a negative huge number.
Okay.
Okay. Yeah, there were several steps in that argument there.
Can we go over 31, please?
You bet. Okay, 31. Okay, 31. T over the sine of t. By the way, what are the directions here? Never mind.
Oh, you got it. Okay.
Oh, well, go ahead. Tell me.
It just says find the vertical asymptotes of any of the graph of the function.
Yeah, and that's what VA means, vertical asymptote. Okay, so T, you got a fraction here. When are we going to have a vertical asymptote? Whenever the sine of t would be 0, right? That's the only thing we can't have. Okay, so when will the sine of an angle be 0? So now this is a trig question. When is sine 0? At 0 degrees, at 180, anytime the angle ends on the x-axis, the sine is going to be of 0 height. All right? So what, in terms of pi, what is 0 degrees? Well, 0 pi. In terms of pi, what is 180 degrees? 1 pi. And you go around further, 360 degrees is 2 pi. So you see how we're getting 0, 1, 2, and you could keep spinning around, 3, 4.
Okay. That makes sense.
So when k is any integer, that's going to give us a sign of 0, and that's why we will have a vertical asymptote there.
So if I had just put down pi for like a test, would that be marked wrong?
No, it's not wrong. It's just not completely correct. Okay. So you would have had, I don't know how I would have judged it, but
partial, okay.
It certainly wouldn't be all wrong.
And then 21 too.
Okay. And sorry, can you tell me what the directions were there?
Yeah, it's the same one. Find the vertical asymptote.
Okay. Thank you. I guess I could have spotted that. All right. So here's our fraction: x squared minus 2x minus 15 over x cubed minus 5x plus x. Okay, so this is a factoring problem. So on top, it's pretty, it wouldn't take you too long to realize it's x minus 5 times x plus 3. Now on the bottom, that's one of those divide and conquer problems.
Mm-hmm.
So hopefully you can see that first you'd factor this first part by x squared times the quantity x minus 5. And the second part, well, you can't, so you can just take 1 out. So that brings you down to this factorization over here, x squared plus 1 times x minus 5. Okay? Now, actually I believe I have this wrong. The x minus 5s cancel, right?
Yeah.
So what does that mean? There's a hole there. So this is actually wrong. There's a hole at x equals 5. And then, how do you solve this? When will x squared plus 1 equal 0? And the answer is never. Because if you subtract 1 from both sides, you have x squared equals negative 1. And you can't take the square root of it. So if you look in the back of the book, I believe it says there are none.
So is there another way to say what there would be though, like the removal or non-removable discontinuity, or something like that?
Well, yeah, there's a hole. So there is removable discontinuity. Okay. But I think that the wording of the question directions was find any asymptotes. Mm-hmm. Was there anything else to the directions?
No, I was just wondering. That makes sense now.
Yeah. So I believe you're going to look, if you look in the back, you should see none. Or NA, I don't know. Anybody have the answer key handy?
Yeah, it does just say no vertical asymptote.
Yeah, yeah. So I had it done right. I just interpreted it wrong. Remember, when a factor cancels, that's not an asymptote. That's a hole. And then the other one in this case was a factor x squared plus 1, but there's no way that can ever equal 0. So nothing came out of that one. Thanks for the question. Any others? Let's see. Did I get any messages off to the side? No. Okay, let's, not hearing any, let's get started on chapter. And by the way, Maria, I am now going to mute you because I was getting feedback from you. Sorry. Turn it back on whenever you want to speak. Okay. All right. So to begin reviewing chapter 2, it's all about limits and their properties. I first put down a couple things that came up before chapter 2 that you would want to hang on to. You should all know how to do a difference quotient. Okay, remember what a difference quotient is? F of x plus h minus f of x all over h. That's a difference quotient. Solving quadratics still becomes an issue. And remember, there's a couple ways to do it. You can use the quadratic formula. You can also use completing the square. And then, as you probably have noticed, trig basics are you can't get rid of those. Those are, even though those came before chapter 2, as you can tell, they're all over the assignments of chapter 2. So, another thing, if hopefully you have this down. How does one factor the difference of two cubes? It's a factoring technique, and it allowed us to solve some of the problems in this chapter. So this is just by the way, is this the difference of two cubes? It is, because 27 is 3 cubed. And how about a to the 18th? 18 is not a cube, but a to the 18th is, because that's a to the 6th times a to the 6th times a to the 6th. And then 64 is 4 cubed, and b to the 6th is b squared cubed. So, okay, and then this is just a reminder. Remember, you always get a binomial and a trinomial. A binomial, cube root of the first term, 3a to the 6th, cube root of the last term, the final term, 4b squared. Mimic the sign. Then comes the trinomial. 3a to the 6th squared is 9a to the 12th. 4b squared squared, 16b to the 4th. And then when you multiply these two, you get 12 a to the 6th b squared. And this middle sign is always the opposite of that first, the sign in the binomial. Anyway, there's the same thing, only this time you have the sum of two cubes. Okay, this is a reminder of how one solves a problem by completing the square. Maybe we should just talk about this briefly. Let me get rid of those pictures again. So, the first thing you got to do is get the 90 out of there. Subtract it from both sides. Then we got a problem. We got a 2 out here. And we can't have anything but a 1. So we got to divide everything through by 2. And this 9/16 is not there yet. Let's make believe that's not there for the moment. Now you've got what? 3 halves. Half of that is 3/4, and 3/4 squared is 9/16. So you notice now we add the 9/16 to both sides. This now is a perfect square trinomial that can be expressed as x plus 3y 3/4. That's half of this term right here. X plus 3/4 squared, and then over here we have some arithmetic to do, common denominator and all that kind of stuff. And then you can take the next step by taking both square roots. So x plus 3/4 equals plus or minus. And this example is bad because you can't take the square root of a negative. So, but the last step then would be to subtract 3/4 from both sides. Whoops. So there is the completing the square technique. And in fact, you remember we even did it on the general quadratic in class that one day. So if you had ax squared plus bx plus c equals 0, you could follow that technique to solve for x. And the final result is good old quadratic formula down there on the bottom. Yeah, and then just I have some difference quotient examples. So I give you a function and I say find the difference quotient. So you want to do, I mean, I don't have it written out here, but what is the difference quotient? It's f of x plus h minus f of x all over h. That's really what you're trying to do. So you notice how I began, I got to find f of x plus h. And that probably is the hardest part of the problem. You got to, everywhere there's an x, you got to plug in an x plus h and hammer it out. You can see with a cube, this is a challenge. Anyway, you finally get, subtract the x plus h from it, and you finally come to this line right here. Now subtract the f of x. And that's what this line is. Nope. That's what this line is doing. And then divide by h. And of course, the whole idea is to get rid of that h. And you should have a way out. You should be able to factor it and do something to cancel that h. Once you've done that, you've got it. You've got your difference quotient. So there's another one, but the difference here is here we had to use conjugates. So I don't know. I will hold off on that, but if you want to see the detail, we can look at it. Another thing, just don't forget, remember, in the book, they always use a double bracket around x to signify the greatest integer function. If I give it on the test, I'm going to use a single bracket like this. So here we have the, yeah. So, and then the only other thing I want to bring up is, remember, you have 3 special limits that you have to know by heart. And those are those 3 there that you see there. Limit as x approaches 0 of the sine of x over x. That's 1. The second one, the limit as x approaches 0 of 1 minus cosine over x. That's 0. And then you got this e guy on the end there. The limit of 1 plus x to the 1 over x power as x approaches 0 is e. Now, this one down below is another form of the one on the right. Okay. So that's what I have for what kind of things that I want to make sure that you have on your agenda as remembering. So that brings us into the review. So I don't know, have you guys looked at the review? And if so, this happens to be the third problem, but so now we're back to you guys on questions again. So what other types of things would you like to ask about as we start getting ready for this test?
Do you want to find a couple examples of a couple more examples of limit problems with either the natural log of x or e the x?
Okay. Well, let's see. Yeah, so here's the review. natural log or e to the x. Well, 36 has a natural log in it. Okay, let's take a look at that 36.
Okay.
It says the limit as x approaches 0 of the natural log of x plus 1 over x plus 1. Wow, for once in our life, we don't have a problem with the denominator, do we?
Mm-mm.
Because as x approaches 0, that's cool. That just approaches 1. Okay, so really, anything over 1 is whatever. So we don't have to really worry about the denominator. So what happens on the top?
It's going to be 0.
Well, what's the net? Yeah, so, and 0 plus 1 is? 1. So what's the natural log of 1?
0.
Yep, that's the answer to 36. Let's go on. Let's see. Well, it's kind of one on 76 there.
Okay.
76 says, in the directions there are, find the vertical asymptotes if there are any. Okay, so the problem is 7e to the negative 3 over x. So I'll just ask you for your any impressions you have of, might there be a vertical asymptote there?
I mean, probably at maybe at 0.
Yep. That's really all there is to that one. Yep. I don't know. You can probably look through your book better than I can. But,
sorry, can you further explain that one? 76 that you just
yeah.
said? Thanks.
So 7e to the negative 3 over x. So Travis said 0 because if x is 0, what's that exponent? Negative 3 over 0. Well, that's undefined. Yep, you got an asymptote there. That's all there is to it. Here, let's take a look at the graph of that. 7e to the negative 3 over x power. Okay. Oh, let's see. 7 times e to the negative 3 over x power. Okay, you can see the graph. And maybe that doesn't give you a real big clue, but you notice it stops at 0. And if we zoom in, I mean, if you try clicking at that point, well, the graph doesn't give you a clue, but you can't, as you can see, you can't plug in 0 because 3 over 0.
I see.
3 over 0 is garbage. So really, when you ask for vertical asymptotes, what are you looking for? You're looking for any kind of a denominator that could be 0, and Travis found it. Now, that denominator happened to be in an exponent, but that doesn't matter. Can you calculate 3 over 0? No, you can't. So that's got to be in it. That's got to be a place where it can't be. I guess it's, yeah. What else? Anyway, those look like the big ones that we found that have to do with natural log or e to the x in this. Oh, here's another one. Here, let's take a look at 61. Trying to make it bigger. Got that. There we go. Move that over. 61. 2e to the greatest integer of x divided by 4. Okay, and you're supposed to tell, is there any place where this is discontinuous?
Would it be at any integer?
Yeah, because you know what greatest integer looks like.
Yeah.
When you're just less than an integer, it rounds it off to that. But as soon as you hit an integer, what does it do? It hops up.
Mm-hmm.
So at every integer, yeah, that's kind of a, you're right. That's going to be a discontinuity. Yep. So I think we've hit the natural log and the E problems from the review.
All right, that's fine. That works.
Anyone else? You may or may not have had a chance to take a good look at the review, but what other things might you want to talk about? You can see the problem that's up here. What's the limit of that as x approaches 3? And the answer is, I don't know until I factor that denominator, right? So when I factor that denominator, I can cancel x plus 3's. And what's the limit as x approaches 3? Well, 3 minus 4 is -1. 1 over -1. And now it's just simple arithmetic. So the limit of that as x approaches 3 is -1. By the way, does this, I just noticed this up here. Does this make sense?
Yeah, it does.
Yeah, it's one of those where who cares what x does? There's no x in the expression, so it doesn't affect it at all. Yeah. So it's just a little reminder of that kind of a thing. Well, I'll just start. I don't know. Let's take let's go to. I'll just take some that I have. Here's number 18. So, what's the limit of that as x approaches 4? Well, again, it's a factoring problem, right? And when you can cancel the t minus 4's, all you have left is what's the limit as x approaches 4 of t plus 4? And that's a whole addition problem. Let's jump further forward. How about 26? Yeah, okay, here's one that has a natural log in it. What's the limit as x approaches 2 of the natural log of x minus 1 squared over the natural log of x minus 1? Well, so this is a natural log law. What's the natural log of something to a power? Remember that? When you take the log of something to a power, it's that power multiplied by the natural log of the thing without the power on it. So natural log of x squared, x minus 1 squared is 2 times the natural log of x minus 1. That's an important log law. Well, once you've got that down, now I've got the top factor 2 times the natural log of x. I can cancel the natural log of x minus 1. Hey, it's just a 2.
Would that have worked out if you had written it natural log of x minus 1 times natural log of x minus 1 on the top?
Yes, it would have.
Okay.
Except that, let's see. So had I written it that way, why would I write it that way? No, that you said the natural log of x minus 1 times the natural log of x minus 1.
Yeah, get rid of the squared.
That's not correct because what this is, that's the only part that's squared.
Oh, okay.
Not the natural log. Okay.
Okay.
So I could that advice would not have worked. So I really had no choice but to use the natural log law to rewrite that numerator like that. So you know what? this reminds me of is you probably should go over your natural log laws again. Anybody else? Question on 26? So let's look at this. This section from 29 to 32. Let's look at 29. It says in the directions, you're given that the limit of f of x as x approaches c is -6. And the limit of g of x as x approaches c is 1/2. So what's the limit of f of x times g of x as x approaches c? Well, you knew those individual limits, right? So you just multiply them, right? -6 times 1/2, -3. So this is due to the really nicely behaving limit laws. Remember, limit laws, I don't think you're going to have to study the limit laws because they work just like you'd think. But the log laws, those don't come as naturally. Here's another section in the review, 39 to 42. Actually, it goes to 48, but find the limit if it exists. If it doesn't exist, tell me why not. So look at 41. Can you tell what I did? So I can't substitute, right? I can't plug in x is 4 because we have an x minus 4 on the bottom. All right? So what am I going to do? It's got a root in it, so I have to use the conjugate method. So I had to multiply top and bottom of this fraction by the conjugate of the top. On top, that gave me an x minus 4. Thankfully, that allowed me to cancel with that x minus 4 on the bottom. Now can I substitute as x approaches 4 from the left? Yeah. Square root of 4 is 2. 2 plus 2 is 4. 1/4. We're just about at the end of time here. I'll just take a peek at another section of the review. Removable, non-removable discontinuities. Find the x values at which, why don't we just take 53, okay? X over x cubed minus x. Does this have any, what kind of discontinuities might it have? Well, especially when you factor the denominator, which I have done here, okay? Right, you can take an x out of there, x times the quantity x squared minus 1. Now, why is I'm trying to think here. Why is 0 removable? Well, you can't have the denominator be 0, right? And if x was 0, that would make the denominator a 0. Okay, why is that removable? I'm going to wait for an answer on that one.
Which part is removable? Same as the x, so you can cross out the x's.
Because you can cancel. That's correct. All right, then what else would make the denominator 0? When x is a 1 or a -1. That one's non-removable. So in other words, x is going to be, at 0, you're going to have a hole in this graph. At 1 and -1, you're going to have an asymptote. And so that's non-removable. Okay, well, we got to start. And we have another day at this tomorrow. Thanks for your questions. You guys are very good at asking questions. Any parting questions before we hang up today?
I'm good.
All right, I think we're going to hang it up. Thank you, and I'll see you tomorrow.